Hi class. We did section 6.3 in class with overhead issues, and here I'm going to set down in our YouTube channel my lecture on section 6.3. 6.3 is the most important section for us for this chapter. It lays down the quantum numbers within an atom. So let's raise this. Okay, we talked about the Bohr model and how the line spectrum of gases came from the transition from one orbital to the next. And after Bohr, there were these following developments towards a theory of quantum mechanics. Particles and waves are very different phenomena in the macroscopic realm, but by 1920s it became increasingly clear that very small pieces of matter follow a different set of rules from those we observe for large objects. The unquestionable separation of waves and particles was no longer a case for the microscopic world. That's just an inference pattern of waves on the surface of a pond. If electromagnetic radiation can have particle-like character, can electrons and other sub-microscopic particles exhibit wave-like character? In 1925, Louis de Broglie extended the wave-particle duality of light that Einstein used to resolve the photoelectric effect paradox to material particles. All right, Einstein used Planck's H to describe the photoelectric effect, and so de Broglie is going to use the same concept to describe the wave-particle duality. So it turns out that the wavelength of light, there is an expression for the momentum of light, and its wavelength is h divided by the momentum. So de Broglie simply extended this to matter, where momentum is the mass times the velocity. So this is de Broglie's formula for the wavelength of a material particle. The de Broglie wavelength is a characteristic of particles, but not electromagnetic radiation. Well, I don't know why they say that, because in this formula they are in fact equivalent. But Davison and Germer used de Broglie's formulation to test to see if electrons had a wavelength, and indeed they were able to diffract through a double slit experiment just like light, if you knew what that wavelength was supposed to be. Bohr had postulated that the electrons as being a particle orbiting the nucleus in quantized orbits. De Broglie argued that Bohr's assumption of quantization can be explained if the electron is considered a circular standing wave. Only an integer number of wavelengths can fit exactly within the orbit. So using de Broglie's wavelength, it turns out that Bohr's quantized orbits matches de Broglie's assumption of the wavelength of light. If the electron is viewed as a wave circling around the nucleus, an integer number of wavelengths must fit into the orbit for the standing wave behavior to be possible. So the dotted line is the circle, and the wavy line is a wave going above and below that midline circle. For a circular orbit of radius r, the circumference is 2 pi r, and so de Broglie's condition is that 2 pi r is equal to n lambda. N equals 1, 2, 3. Davison and Germer demonstrated experimentally that electrons can exhibit wave-like behavior. They showed that electrons traveling through a regular atomic pattern in a crystal produced an interference pattern. The interference pattern is strikingly similar to the interference patterns for light. And this is, although this shows a double slit, they actually use the nickel crystal, which has slits in it. Anyway, but this is essentially what the Davison-Germer experiment did. The interference pattern for electrons passing through very closely spaced slits demonstrates that quantum particles, such as electrons, can exhibit wave-like behavior. The experimental results illustrated here demonstrate the wave-particle duality in electrons. Thus, it appears that while the electrons are small, localized particles, their motion does not follow the equations of motions implied by classical mechanics. Instead, some type of wave equation governs a probability distribution for an electron's motion. Thus, the wave-particle duality first observed with photons is actually a fundamental behavior intrinsic to all quantum particles. Werner Heisenberg determined that there is a fundamental limit to how accurately one can measure both a particle's position and its motion simultaneously. The more accurately we measure a momentum of a particle, the less accurately we can determine its position at that time, and vice versa. The Heisenberg uncertainty principle, it is fundamentally impossible to determine simultaneously and exactly both the momentum and the position of a particle. Delta x, which is the uncertainty in the position, and delta p sub x is the momentum in the x direction. That product is less than, is always greater than h bar over 2. Now h bar is h divided by 2 pi. Anyway, there's a limit, whatever it happens to be. It's based on h here. And as I mentioned in class, this also implies that there's a ground state to an atom, because if the electron and the proton were allowed to fall infinitely close to one another, they would release an infinite amount of energy. But we don't see that. We see that there is a ground state in the hydrogen spectrum and in the spectrum of all gases, that the electron falls only a certain distance to the proton, and then it is unable to go closer to the proton. And this is implied that when delta x gets very small, the variation in the velocities of the particle is great. So if it's trapped as it goes down towards the proton, its delta x gets smaller, but its velocity gets greater and it escapes from the proton. And so there's a balance here between the distance at which it's found and the velocity at which it's escaping and falling back to the proton, and it has a finite value. It's always above a certain finite value. Erwin Schrödinger extended de Broglie's work by incorporating the de Broglie relation into a wave equation. Today, this equation is known as the Schrödinger equation, or Schrödinger equation. Schrödinger properly thought of the electron in terms of a three-dimensional stationary wave, or wave function, represented by the Greek letter psi. A few years later, Max Born said that electrons are still particles, so the wave represented by psi are not physical waves, but instead are complex probability amplitudes. The square of the magnitude of a wave function describes the probability of the quantum particle being present near a certain location in space. Wave functions can be used to determine the distribution of an electron's density with respect to the nucleus in an atom. The Schrödinger equation is written in terms of an operator acting on this function in all of space, and it returns simply a number times that function. This operator can have derivatives and other energies associated with it, but it yields a single value multiplied by this. This is called an eigenvalue problem, and that's the way it is. It's still difficult to solve, especially for repelling electrons, but they have ways of approximating this with an infinite number of trial wave functions, and it takes a lot of computing to get at numbers that are reasonable. Psi is the wave function of the particle, and E is the total energy of the particle. Schrödinger's work, as well as that of Heisenberg and many other scientists following in their footsteps, is generally referred to as quantum mechanics. Electrons and atoms can exist only in discrete energy levels, but not between them. The energy of an electron in an atom is quantized. The energy can be equal only to a certain specific values and can jump from one energy level to another, but not transition smoothly or stay between these levels. And this is all similar to the Bohr atom. The energy levels are labeled with an N value, where N equals 1, 2, 3, just like in the Bohr atom. Generally speaking, the energy of an electron in an atom is greater for larger values of N. N is referred to as the principal quantum number, or shell number. The principal quantum number defines the location of the energy level and is similar in concept to the Bohr model. So that's the different shells of energy of electrons moving out. The principal quantum number is one of the 3 quantum numbers, actually 4, used to characterize an orbital. An atomic orbital is a general region in an atom that an electron is most probable to reside. An atomic orbital is distinct from an orbit, meaning we're using the word orbital to be a solution to Schrödinger's equation, whereas an orbit was what was in the Bohr model, where something is actually going around something else. The quantum mechanical model specifies the probability of finding an electron in a 3-dimensional space around the nucleus. Now there are 4 quantum numbers that give the address to each electron in the atom. The second of these is the angular momentum quantum number with an L. It is an integer that defines the shape of the orbital. We say that L takes on values of 0, 1, 2, all the way up to n minus 1. So if n equals 1, L can only be 0. If n equals 2, L can equal 0 and 1, and so on and so forth. For an orbital with n equals 1, L equals 0. For an orbital with n equals 2, L equals 0 and 1. Orbitals with the same value of L form a subshell. Well, actually they're leaving that out. Orbitals with the same values of L and N form a subshell. So there are 3 L equal 2 orbitals for n equals I'm sorry, there are 3 n equal, L equals, whatever. Let's continue. Instead of using numbers, the angular momentum quantum numbers are often designated by letters. L equals 0 is called an s orbital, where s means spherical. For L equals 1 is a p orbital. P doesn't mean anything in English, really, but we'll say dumbbell-shaped orbital. For L equals 2 are the d orbitals. The d, I drew an X-shaped dumbbell, or a four-leaf clover-shaped dumbbell, and most of the d orbitals are four-leaf clover-shaped. But there is one of them that is like a dumbbell that goes through a donut, and we'll see that in a minute. And then L equals 3 are the f orbitals, and the f orbitals are just like a bunch of balloons all tied together at their knots. There are certain distances from the nucleus at which the probability density of finding an electron located in a particular orbital is 0. Okay, these are called the radial nodes. This is, just know the term radial node. It's not especially important. It's what they're pointing out here is that the electron density for the 2s actually has internal regions where the electron density goes to 0. So there's this shell in the middle where the 2s electron does not visit that shell at all. Oh, of course, it gets from outside that shell to inside that shell, but it doesn't spend any time at all on that particular spherical surface. It's not critical to what we're dealing with here. The S subshell has a spherical shape, the P subshell has a dumbbell shape, and the D and the F orbitals are more complex. These shapes represent the three-dimensional regions where the electron is likely to be found. Okay, these are the S, P, and D and F orbitals. This is an S orbital, it's a sphere. And what they're showing here is the wave function, but not the probability. When these things get squared, they get much more elongated. So this is the dumbbell shape that we were talking about. Consistent, as I said, the Schrodinger equation basically models the electron based on the vibrations of a sphere. And so this is the sphere pulsating from one side to the other. Now this has a phase, and we're just arbitrarily calling one phase blue and one phase red. It has nothing to do with charges. It's just the phase of the wave function. And the p orbital can line up along the x direction, the y direction, and the z direction. The d orbital, as I say here, looks like a four-leaf clover, or at least it would look more like a four-leaf clover in the probability distribution. And here it is with the center pointed along the z direction, the center along the y direction, and the center along the x direction. And this one's staggered, and this one is odd. This is the one that I said looks like a dumbbell that goes through a donut. Most of the elements that we're going to be dealing with have s orbitals, p orbitals, and d orbitals. The compound that the atom that has the most number of compounds is carbon. It forms organic chemistry, and the organic chemistry of carbon deals with the s and the p orbitals, which is what chemists deal with most of all. The transition metals deal with the d orbitals, and the rare earths and actinides deal with the f orbitals. The f orbitals are so complicated that one doesn't even bother with visualizing them. And we move on. If an orbital has an angular momentum, L, that's not equal to 0, then this orbital can point in different directions. The magnetic quantum number M M sub L specifies the orientation of the orbital in space. So the value of M sub L depends on the value of L. It can be minus L all the way up to 0 and then up to plus L. There are 2 L plus 1 orbitals with the same L value. So 1s orbital for L equals 1. There are 3 p orbitals for L equals, there's 1s orbital for L equals 0. There are 3 p orbitals for L equals 1. There are 5 d orbitals for L equals 2, and there are 7 f orbitals for L equals 3. When referring to an orbital, usually both the n value and the letter designation for L are reported. So it's for example, it's the 2s orbital and the 3p orbital. In the case of a hydrogen atom, energies of all the orbitals within the same n value are the same. We call that degenerate energy levels. However, in atoms with more than one electron, this degeneracy is eliminated by electron-electron interactions. Orbitals that belong to different subshells have different energies. Orbitals with the same subshell are still degenerate and have the same energy. Okay, so all the p orbitals have the same energy. And certainly orbitals that belong to different subshells have different energies. All right, this is the magic diagram that came out of the Schrödinger equation. And that is that 1s is our ground state, 2s has a higher energy than that. When you have a multi-electron atom, 2p is slightly higher in energy than 2s. 3s is higher than all of that, and 3p is higher than that, and 3d is higher than that. But here is the kicker. 4s actually comes down below 3d, and then 4p is higher than everything else. So this is the diagram we use to fill in the electron configuration of atoms in the periodic table. The first, hold on, let's go back to that. That is figure 6.22. We're going to use this over and over again. And we'll point out that 6.22 is actually inherent in the periodic table that hangs in our classroom. You can actually see it and read it off directly from the periodic table. The first 3 quantum numbers, n, l, and m sub l, define the region of space where an electron is most likely to be located. The electron spin is a different kind of property. Electron spin describes an intrinsic electron rotating or spinning. An electron can only spin in one of 2 quantized states. The spin of the electron can be either plus a half or minus a half. It's represented with m sub s. Now, why it's a half and not 1, as I said in class, is way beyond the scope of this class. It has to do with particle physics and our models of these kind of spins. and this is what they call, these are what they call fermions. If it had spin 0, it'd be a boson, or any integer spin, and it has to do with the statistics. It's way beyond the scope of this class, except the fact that we use plus 1/2 and minus 1/2. Any electron, regardless of the atomic orbital it is located in, can only have one of these two values of the spin quantum number. Electrons with spin plus or minus 1/2 in an external magnetic field. This was also an experiment that was done. It was with silver atoms, and physically you send a beam of atoms that have a single up or down spin, and they will either go in one direction or the other in a magnetic field, and so you can actually see these spins. Now, why is it not part way? Why doesn't one of these things veer somewhere in the middle? That's the nature of quantum mechanics. It's either one way or the other. An electron in an atom is completely described by 4 quantum numbers: N, L, M sub L, and M sub S. That is its address within the atom. Wolfgang Pauli, an Austrian physicist, formulated a general principle, the Pauli exclusion principle. No two electrons in the same atom can have exactly the same set of all 4 quantum numbers. Whether he said that or not, this is what is observed, is that the electrons, as they enter the atom, go into these addresses, starting with the lowest energy address, and and fill up the orbitals of the atom. So the last electron goes into these higher energy orbitals. This building up of the electrons within the atom is given a German name, the building principle in English. In German, it's the Aufbau principle. And you can think of it as cars filling a parking lot. Each parking space is designated by 4 quantum numbers. Once an electron car is parked in that parking space, nobody else can park there. Electrons can share the same orbital, the same set of quantum numbers, N, L, and M sub L, but only if they have different M sub S numbers. Since the spin quantum number can have only 2 values, plus or minus 1/2, no more than 2 electrons can occupy the same orbital. If 2 electrons are located in the same orbital, they must have opposite spins. Quantum numbers, their properties and significance. So this is an important table. This is what we need to know. The principal quantum number N, 1, 2, 3, 4. The angular momentum L can be 0 to N minus 1. And the magnetic quantum number can be from minus L to plus L. And the spin quantum number, M sub S, can only be plus 1/2 and minus 1/2. And that's it for this section. Thank you very much for listening. Let me save it.